Okay, so it's a great pleasure to introduce the next speaker, Margarita Veshchezerova. So Margarita is now working at Tetra-Opt, and so you are going to talk about quantum, hybrid, and quantum-inspired optimization.
Yes, thank you very much for the introduction, and I will do a longer introduction for those who don't know me. So I finished my PhD 4 months ago. I was supervised by Simon down here and by a supervisor from EDF who is retired now. And my topic was the quantum approaches for combinatorial optimization. And then I followed in Terra Quantum with exactly the same topic where I tried to do the combinatorial optimization with quantum approaches. So today I will present you this written on the slide, quantum hybrid, quantum inspired optimization, in a way we understand it at Terra Quantum. So there are different ways to speak about this. And let's get it. So first of all, I'd like to give you a very large scope of what we do at Terra Quantum. So we have multiple activities in quantum computing. We are more focused on quantum software rather than the quantum hardware, but we have some activity in the hardware as well. So I will start by the end of the list, so by the cryptography, because it's the most hardware related. So for the cryptography side, we have a solution for the random number generator. I've seen it, it's a small box, so it's nice thinking that allows you to have the true randomness, useful for cryptography. We also have a physical setup which allows to distribute quantum keys, and which works with optical fiber, and which actually works on large distances. And this is not the traditional QKD protocol, but a different one, which doesn't have troubles when you go to several hundred of kilometers. So this is what concerns cryptography. We also have activities in machine learning, in particular in hybrid, quantum, classical neural networks. We have an expertise in reinforcement learning, which we try to move now in the quantum domain with more or less success, let's say. But we also leverage the methods from reinforcement learning for the optimization. And now the cream of the cream, I don't know the English expression, but it's the optimization part. So in optimization, we focus on everything that is possible to do things better. So the first thing is we try to take existing quantum approaches and make them useful. So for instance, when I say make them useful, we want to find the very exact place when the application of quantum approaches can bring us an advantage. And to do so, we usually use the hybrid routines, in which we have a bigger procedure, which decomposes problems, which subtracts some sub-problems, and which we can then solve with some well-adapted quantum solvers. So we also work on the heart of quantum solvers by developing the variational quantum algorithms, like the ones that were presented by the previous speakers, the QOA, the VQA, and so on. And the last but not least, we try to leverage our understanding of how works the quantum physics in order to design and suggest new methods for the optimization. And when I say how works quantum physics, I actually mean how works the mathematics that we use to describe quantum physics. And this is what we call the quantum-inspired algorithms. And in this presentation, I will speak about these guys. So I'll start by given a broad vision of our understanding of hybrid quantum classical pipelines. So what are the different ways to hybridize and so on. So then I will present these variational quantum algorithms that we developed at Terra Quantum, which we call the QYANG, and which in a sense is a little bit different of what people usually do. And then I actually decided to do a bigger section about quantum inspired, because no one else, as far as I understand, is going to speak about quantum inspired. And I will speak about the quantum inspired method, which we call the Tetra-Opt method. And this method is based on what is called the transit train decomposition. So I will introduce what it is, the transit train decomposition. And this method is well suited to optimize the function with both discrete and continuous variables. And I will show how it works. So I'll go a little bit in details down there. So then I will present a couple of use cases, one in depth, so the shape optimization and neural net optimization, molecular docking, and the solution of partial differential equation just a big picture. So I will show how this method can actually be useful for practical problems. So now what happens when you try to the whole idea of hybrid methods is to make the NISQ quantum machines useful. So for instance, NISQ is a noisy, intermediate, small scale, yes, noisy intermediate scale quantum computer. Yeah, so you have all this stuff which enters. So the first one, for instance, is intermediate scales, which means that you don't have so many qubits, and you can't optimize the problem over a huge amount of variables. So the first thing that you have to think about is how to feed your problem to a small quantum hardware, and basically, you have to reduce the sizes of the problems that you delegate, and we consider different methods of doing so. So, for instance, one of the directions is what I call the cat set decomposition. So, in which you fix some of your variables and you optimize the rest of the problem on the quantum computer. Yesterday, I got an inspiration from this pop music presentation about this large-scale neighborhood search when you subtract a cluster of variables and then you re-optimize your problem on this cluster of variables. So it's a future work, I guess. The second thing is that, okay, let's imagine we can solve some QBO problems right now. So now usually your optimization problem from the industry is not a QBO problem. So you can use some naive techniques in order to go from your formulation to a QBO formulation, penalization of constraints, discretization of continuous variables, and so on and so on. But it's not something that always makes sense. So you don't want to do, for instance, the shortest path problem. You can also model it as a QBO. But what for? If you can solve your shortest path problem with a Dijkstra algorithm rapidly, polynomially, and so on. And for QBO, you have only heuristic solutions and maybe not always the best ones. So we try to attack this problem, this decomposition. We try to use the decomposition to, first of all, extract from our bigger problems some subproblems which can be modeled as QBOs, and for which it makes sense to model them as QBOs. And this is something which we actually almost often are able to do. And there are a couple of things that I mentioned here as techniques. So for instance, when we designed this hybrid procedure, we tried to delegate inequalities to different routines in the QBO instead of just putting them in the QBO. We also use a lot the reformulation, and it's not the same reformulation as the one mentioned by the previous speaker, but it's a reformulation when you separate your problem on two different sides. And like the one side tackles your inequality constraints or your continuous variables, also on, and the other part is the QBO, and they interact with each other. And like for instance, we have a technique which is inspired from column generation, which allows to separate this problem on two different sides. And now the very last thing is that can we have a quantum advantage with this approach? So first of all, we need to find a way to decompose our problem and find this QBO sub-problem. But then in order to get the quantum advantage, we actually need to get a quantum advantage on the QBO problem itself. And as we have seen this morning with a wonderful talk about meta-heuristics, it's kind of challenging because meta-heuristics are super performant. They existed for a long time, and today there is nothing that demonstrates that quantum computers will actually going to be able in practice to beat these good QBO solvers. So we are struggling here, everyone is struggling here. And I just mentioned a reference, which might be interesting for some of you, which compares the quantum annealer to a simulated annealer on a very specific designed problem in order to, that favors the D-wave quantum annealer, and they've observed the tunneling. But I mean, this problem, if you do not restrict yourself to solve it with simulated annealing as a classical benchmark, but instead you choose another classical benchmark, you already beaten, you find the optimal solution and no troubles. So it's just for the general culture. So now let's move to the quantum routines, which we design Terra Quantum. So the algorithm which I'm going to present is a variational algorithm. So in variational algorithm, you suggest a family of circuits, and this family of circuits is able to prepare a family of probability distribution. And out of this family, you want to select one member which you're going to use to sample your solution. And usually you are given some loss function, which depend on the problems that you want to solve, which tells you, okay, this circuit is good, this circuit is bad, or this circuit is better or worse than another. And this variational technique is in heart of two very well-known algorithms, which is variational quantum engine solver and QOA. And what is the key difference between these guys and our solution is that in variational quantum solver and in QOA, you get one qubit per variable. So, and then once your quantum circuit is executed, you just measure your qubits, and then you get a solution, an approximate solution to your optimization problem. What we do instead in the QN is that we actually separate our qubits on what I call register and what I call ancilla. And the register is here to tell which variable we are talking about. So it is something which encodes the index of the variable, and encoding the index requires if we use the binary expansion, requires just the logarithm of the number of variables, like the number of qubits is equal to the logarithm of number of variables, and then we get one extra qubit to tell what value our the corresponding variable takes. So this allows to use exponentially less qubits than in what we use in traditional encoding. However, like you need to read out the value for each of your qubit in the end, you still have the runtime, which is proportional to the number of variables. So this compression is useful to at least try to address your problems on these small quantum computers, because like with this QN, we were able to solve the MaxCat with 256 variables. Yeah, so, and 256 is unimaginable for like the actual quantum computer and so on. So, yeah, so this is a big picture. Now let's go to the quantum inspired. So in quantum inspired, I'd like to present a solution that we called the Tetra-Opt. So this Tetra-Opt algorithm is based on, I will explain what it is. It's tensor train decomposition. And this solver is able to optimize functions which are given as a black box. So we do not know anything about them. We just have an oracle which tells, okay, for these values, for this variable assignment, we get this value, and so on and so on. And so usually this black box optimization is a very challenging task. It's often done with some methods like a grid search. You just evaluate your function in many different points. And in a sense, the Tetra-Opt does something which is similar, but in a more intelligent way than in a grid search. So obviously, this method doesn't use gradients because you have the access to the black box function. It is initially designed to address variables over discrete domains. However, if we have continuous variables, we can discretize them on a grid, and then search the optimum on these like discretized values, and the grid delta can be pretty small, so we do not have to discretize with a very large grid. So and a particularity of this approach is that it's actually really good for parallelization. So for instance, the grid search for the optimum is also good for parallelization. You just evaluate your function in like different points of your search space and so on. And this is a property which is preserved when you go to the Tetra-Opt. And it is particularly interesting when your black box function, when your function evaluation requires a significant time. So for instance, let's imagine that the function that you want to optimize, actually to compute it, you need 20 seconds because it's a simulation of some difficult physical process. And at that point, if you can't evaluate your function in parallel in different variable assignment, it's actually quite useful, and it can save you a lot of time. So now, let me, if you are interested in math, it's a time to wake up, because previously it was more about like strategy, vision, and so on, and now it's how the things works in reality. So the tensor train decomposition is a low rank approximation of the tensor, in short. However, in order to understand it, the easiest path to follow is to start from the matrix. Matrix is a two-dimensional tensor. So, and if we have a function which has two variables, we can write its values in a matrix and obtain a two-dimensional matrix, as you can see on the slide. And then out of this matrix, we can compute, using a single variable decomposition, a low-rank approximation, where we approximate the matrix with a matrix of a small array. And we can do it, but is it always the best way to do it? So the best, why it might be not the best way to do the things is because in order to compute the single variable decomposition, you actually need to know the value of your function in every single point of your search space. And what we suggest to do instead is to use the algorithm which is called the max volume algorithm, which is more time efficient, in which significantly reduce the number of functional evaluations that you need. So when you go from this 2-dimension to a higher dimension, you add extra variables. So now let's say that a function over d discrete variables, let's say that each variable can take n different values. It can be represented as a tensor with n power d elements. So a tensor where you have d different directions and a total amount of elements n power d. And this is an extremely huge amount. So what we suggest to do instead is we suggest to use a compressed representation of this high tensor. So for instance, for each of the variables, except the first and the last, to which I'm going to come back, we find, like, let's call the size, the number of possible values for the variable en. So we find n different R times R matrices, and we just put them in the package. So then for the first and the last, we find just columns and the rows. And what is the correspondence is that the value of your tensor now is approximated by the multiplication of the corresponding columns and the matrices. So for instance, if you take, like here, you can see what should you multiply. If you take the first, the second discrete value for the first variable, so you can see it in the red. So you have the second value. Then you multiply, and for the second variable, you took the very last value, and then for the last value, you took the first value, and then you just multiply them, and you obtain one single number, and this number approximates the values or the value of our function in the corresponding point. So it is an approximation, and this approximation is useful because it allows to go from n power d elements in the initial tensor to r squared times d times n variables in this compressed representation. So this is the low rank approximation. Now the question is, how do we build it? So the last time I mentioned that we can do it with a singular value decomposition, but now, like singular value decomposition, we need to do the evaluation in every point. And can we do something better? So it turns out that we can. So for instance, we can approximate a two-dimensional matrix with a product of sum of its columns, sum of its rows, and the inverse of the matrix in the intersection of its rows and its columns. And there is a nice property from the linear algebra that if this small submatrix, the intersection of selected rows and selected columns, is the submatrix of what we call the maximum volume, the approximation error is not really high. So I give the bound here for the approximation error. So it depends on the rank of approximation that we use. It also depends on the singular values of the initial matrix that you approximate. But the maximum value is actually a submatrix which has the biggest possible modulus of the determinant between all the matrices, all the submatrices of size R times R. So now, and basically you would like to find these small submatrices and take corresponding columns and take corresponding rows, and you get your decomposition. You're done. Now, how do you find this submatrix of the maximum volume? No, actually, now we are not speaking about this. We are speaking about something else. We are speaking about that actually as a byproduct of a search of this submatrix of the maximum volume, what we can obtain is that we can obtain an approximate optimum for our d-dimensional d-dimensional function. So, for instance, if we have a function over two variables, which take values in some discrete sets, and then we found this maximum volume submatrix of size R times R, and it turns out that the maximal element in this small submatrix is an approximate element of the maximum element in the initial big matrix. So we significantly reduce the size of the problems that of the evaluation of the points in which we evaluate our function. So now the question is, how do we find this maximum volume submatrix? So what we know how to do. So let's imagine that we have this like tall tall matrix in which we have in rows and R columns, and we want to find an R times R maximum volume submatrix in it. And it turns out that we know how to do it. This algorithm is called max_vol, so that's why the whole algorithm is called max_vol. It's not really difficult. It's a greedy procedure. You can find it on references and so on. I'm not going to go into details, but now we don't have a tall matrix with R columns, but we have a big matrix with M columns or whatever, and we need to find the maximum volume matrix in this guy. So what we do, we suggest the procedure which we call the alternating direction, in which at the beginning we select some random columns, R random columns. So then we evaluate our function in all possible assignments for the first value for these two columns. And out of this evaluation, we select the, like here we apply this algorithm and we find the maximum volume submatrix, R to R submatrix, in this, for this like R columns that we selected randomly. And then we take the rows that correspond to this maximum volume submatrix. And we redo this process backwards. So now we have rows. Now we search for the maximum volume submatrix in these rows. We find the columns that correspond to this maximum volume submatrix. We take these columns and we iterate until they converge. I'm not sure that it's super clear because we have these faces, but I hope it's a little bit clearer at least. So now what happens that when we go to higher number to higher dimension? So now we don't have only two variables, we have many variables. How do we transform this technique? And basically what we suggest to do is we suggest to use some kind of subsequent unfolding of our tensor. So first of all, if we have a tensor of d dimensions, we can rearrange it in a kind of matrix in which we have, let's say, n rows and n times d minus 1 columns. And then we can randomly select two columns in there. So in terms of the optimization problem, what it would be is that for each of our variables from the second to the last, we selected some random values. So we selected some random values, and then we evaluated for these random values of all resting variables, what value take our function for different values of the first variable. So now we got these two columns. And in these two columns, we search the maximum volume submatrix, and we do exactly the same way, the same thing as before. But now we can't actually reiterate a search for the maximum volume submatrix in this row matrix, in this long row matrix, because it's just too big. It's just too big because we fixed only the value for the first variable, but we have all possible values for the second, third, and so on and so on. So how do we manage it? We manage it by, one more time, reshaping our matrix. So we reshape our matrix, and now we have we keep these values of R that we selected before, these values of the first variables that we selected before, but then we keep all possible values for the second variable, and we maintain the rest from the third to the last variable in our second dimension of the matrix. And we redo this random selection of columns, and then from this random selection of the columns, we select the rows that we're going to privilege. We keep these rows, and then we continue and continue and so on. And we can do it one way, and we can do it backwards, and that way we approximate these maximum values of matrix of a bigger matrix. So this is how the algorithm works. So now what I'd like to say is that this algorithm actually do two things. Let's go back. This algorithm do two things. So the first, it helps us to construct the low rank approximation of our tensor. But the second thing that it is able to do is to find the optimal element. So every time we evaluate our function, we save the values that we obtain, and then we keep the best values that we meet during this optimization process in as the optimal solution, temporal optimal solution. And then we return this value once the optimization is done. So we basically do some kind of a grid search where we do not evaluate our function in every point of the grid, but in some specifically selected ones that corresponds to this maximum volume procedure. And then we return the best value obtained during the optimization process. So now we have this tensor train decomposition. We found during the process of constructing this tensor train decomposition the optimal element, but what we can also do with tensor train decomposition. So it turns out that we can also multiply it by constants, add the constant number, add two different tensor trains element-wise, and make an element-wise multiplication, and then compute the sum of all elements in your matrix. So this all procedures actually increase the rank of our tensor, where the rank is the size of this small submatrix that we use in between. But it can be done. So, and it can be done without unfolding your tensor. So you do not need to go from your tensor back to the function representation or whatsoever, then multiply. So let's imagine that you constructed tensor train representation for two different functions. So then, in order to obtain a tensor train representation for their product or for their sum, you do not need to redo the whole process and take in as a function the multiplication or the sum, but you can just take your two tensor train representations and then add them or multiply element-wise multiply them or whatsoever. So now how it can be useful. Second opportunity to wake up for people who didn't like math. So now we speak about the applications. So we had a problem in which we wanted to optimize the shape of what is called a mixer. So a mixer is something which has two entries by which the two different liquids arrive. So it can be like water and some chemicals or so on. And then this mixture, these two liquids meet in the middle point, and then they go down. And like the idea is to find the shape of this mixture, so such that the distribution of your of the density of different components is the most uniform as possible around the vertical around the part of the mixed liquid. So you want to do it, and maybe you had an opportunity to live in an apartment in which you had cold water, hot water, and they were not mixing really well, and you were really suffering because either you have everything which is super cold, or then you just turn your you just tune it a little bit, and suddenly you got burned or whatsoever. So it is an important problem, even out of the chemical industry, but in the chemical industry, it's like an extremely important problem. And why it is so difficult is that every time, let's say you suggested the configuration, you are happy and so on, and now you want to know how good is this configuration, and you have the simulation software which evaluates how good is your configuration and so on. You can wait for many hours to get the result out of it. So each evaluation of each suggested configuration is an expensive task. You can simplify it a little bit, but it's a long process. So you can't just say, okay, I have my numerical software, I can model whatever I want, so I will just try different configurations. I will try all possible configurations, let's say, and then I get my solution. It takes time. So usually the grid search, like for this particular problem, it's maybe not the worst one because you don't have so many parameters, but let's say you just add one extra parameters and then you multiply the number of points that you need, in which you need to evaluate your function. So the grid search has this very bad scaling on the number of your variables. And so usually what you do is you do the method which is called Bayesian optimization. And this Bayesian optimization is not an easy method to follow. So, and this is something which is critical, is that comparing to the grid search, we do not do evaluation in every possible point of the grid, but compared to the Bayesian optimization, we can do these evaluations in parallel because Bayesian optimization is a sequential method. In Bayesian optimization, you evaluate your function in one you start with some initial evaluation, so then you approximate your function, and then you at the same time search the minimum and improve your approximation by evaluating your function in different points. And but you have to do it sequentially, while with the Tetra-Opt, you can, like, once you've selected your columns, you can evaluate your function in every element of your selected columns in parallel, and there is no problem with that. So, and with this idea of parallelism in hand, we can see that what we obtained is that we obtained a much better cost values in much lower time. So, and here the error bars actually are the error bars of different launches because we relaunched as two methods are kind of heuristic. When you relaunch them with a different random number seed, you get different results. And but then, in average, the Tetra-Opt method is faster and gets better results. So, one more time, due to the parallelism. And this can be applied in different problems. So especially in problems of the black box optimization. So for instance, if you try, we personally tried and made a paper out of it to solve the problem of protein Docker, in which you had two different proteins, and you want to readjust the position of one of them in order to maximize some score function. So you have, if you imagine that your proteins are rigid, you need to decide where you place it and how you rotate it. So you have 7 different parameters to optimize. And then we were able to obtain better results than other methods. So one is different implementations than ours of the same of the similar approach. So the tether chain decomposition. And the last one is a glow warm swarm optimization. Glow warm. Okay, so it's a swarm kind of swarm optimization method to which we benchmarked our approach, and we obtained higher scores. So we obtained better configurations for our problem. So where we also use this technique is in optimization of parameters of neural networks. So both in the configuration of neural networks and the meta parameters that you need to get good neural models. And we've observed that we have, with our search, which is done by Tetra-Opt, a better accuracy of the resulting neural network. The use case that we considered were the neural networks for the computer vision. So, and we think that by using our method, you can automate this search for good architecture and good meta parameters for the model. And this is an advanced topic, but it can also be used to compress your neural network afterwards by using this tensor train representation, but I'm not going into details about it. And it turns out that you can also use this representation in terms of tensor trains in order to accelerate the simulation of evolution under some partial differential equations. So by going from the traditional finite element method to tensor train version of finite element method, and it helps you to save the running time. So these are the different other applications that you can use. But basically, like for optimization, it's going to be the black box optimization. People also have done QBO with this, but not us up to now. So now I was still speaking that the quantum inspired. So what is the quantum part of this whole stuff? So first of all, for people who are aware, who are familiar with quantum many-body physics, this tensor train format was used to represent the ground states of quantum many-body systems. And but here what we see is that we can go from this tensor train representation, and we can actually use it to represent maybe some analytical function and so on. We can encode them in a quantum state. So for instance, it's a really difficult problem. Many people thought about it. So how you go from classical data and how you put it in your vector, in your quantum vector, in your amplitudes and so on. So if you just go value by value and you put it inside the your quantum state, you're going to have an exponential size of the circuit which is required to do this operation. But what we suggest to do instead is that first of all, you compute a tensor train representation, and then we suggest that the state that corresponds to this tensor train is actually prepared by a variational circuit. So we design a variational circuit, we define a loss function on it, and we get the tensor train representation. Like here, I'm giving an example of a function for which we discretized the, so it's a continuous analytical function for which we discretized the search space for the variable value. It's a one-dimensional problem, and then we move the values of this function in the amplitudes of our quantum state by using this variational circuit. And so we believe that one day we are working on it now. So how using this quantum state representing our tensor train, how we can use it to do a better optimization. Okay, so I'm done. Thank you for your attention.
Thank you very much. Any question?
Wait, I have a question.
Good.
Did you understand anything or not at all? Like you were looking like you paid attention, so.
We made it.
Okay. Did you understand anything?
Yes.
Okay, great. That's because when people do not ask questions, there may be many reasons for it. So.
Okay, I can start.
Okay.
So at the beginning, when you have this encoding of qubits, this compression.
Yeah.
So you have a logarithmic number of qubits.
Mm-hmm.
So can you do a threshold? So it's
you're speaking about QN.
So here the green part is a little bit larger. If you have more space, you can use a larger green part and maybe a smaller red part. And is there a trade-off between the two? How to choose these? And
yeah, so the red part is something which depends on how many variables do you have in your problem. So you need to encode the index. You have 256 variables. You take logarithm of it, which I don't remember what exact power of 2 it is. So and you need this many qubits to say what variable your amplitude corresponds to. So this is an amplitude encoding. But for this green part, indeed, you can have a larger number of functional variables. And this is an ongoing work in which we do not encode the register of only one qubit, but we encode the pairs of qubits. So our register indicates which pair we are speaking about, and the values of our answers are the values of two variables in our pair. And this initial model is not really like we had very good results in MaxCut, but it's not really able to capture these pair interactions between two different variables. But if we use this larger encoding where the register corresponds to the pair, indicates the pair of the variables, and the ancilos now we have two, so one for the first, one for the second. We can like increase the performance of the method. And actually, yeah, no, I will not say it. I'm not really sure of what I was about to say. Okay.
Another question?
Okay, good.
So thanks again.
Thank you for your attention.